In this lecture, we will discuss a classification technique called discriminant analysis, which has been used for decades in academic research, but now is widely accepted by the analytics community as a model-driven technique for classification. We will first go over the key concepts related to discriminant analysis, which is somewhat related to the principal component analysis we discussed before. Then we will discuss a new distance measure called the statistical distance, also called Mahalanobis distance, named after its creator, which is used in discriminant analysis. Understanding this distance measure, other than the commonly used Euclidean distance, would give you more ammunition when dealing with any analytics techniques that use distance measures. We will then discuss how discriminant analysis classifies observations into classes using what is called classification function, and how the classification functions would lead to predicted probability of class membership. Finally, we will discuss the assumptions of discriminant analysis, as it is a classic model-driven technique, and then any practical considerations for dealing with uneven class distribution and misclassification costs. Like any other techniques, we will also go over a number of cases to illustrate how the technique is used to solve real-life analytics problems. Discriminant analysis is a classical statistical technique for classification that is model-driven, meaning that a model in the form of mathematical function will be produced by the technique for classifying observations, as in the case of logistic regression. The dependent or target variable for discriminant analysis is categorical or classes, and its independent variables are usually numeric, but can also be dummy variables if they are categorical. The technique can be used for research, classification, and profiling. When discriminant analysis is used for research as a statistical tool, the questions that the researcher tends to ask are the groups different? And on which variables are the groups most different? For example, 3 categories of computers possess various attributes. Using discriminant analysis, we can answer the question of whether these 3 categories of computers are really or statistically different, and if they are, which attributes best help differentiate the categories. In analytics, we are most interested in discriminant analysis' ability to classify future observations in the correct categories. For example, whether a stock is a buy, hold, or sell, classifying organisms into species, classifying patients as candidates for treatment or not, or classifying potential customers as early adopters, late adopters, or non-adopters. This use of discriminant analysis will be the focus of our discussion here, and the examples we use will demonstrate such application of discriminant analysis. The third use of discriminant analysis is profiling, which highlights aspects that distinguish the different classes. For example, marketers may ask themselves what characteristics make buyers and non-buyers of a certain product different. We will touch on this subject in our lecture to show how discriminant analysis ranks the importance of attributes that differentiate observations that belong to different categories. It is important to understand that discriminant analysis is a supervised data mining technique, meaning that the outcome classes are predefined, and we know the actual classes of the historical cases used to build the model. The predictive accuracy of the model is assessed using the misclassification rate of a holdout sample. However, sometimes there may not be predefined classes. For example, we may not know beforehand how many different types of customers we have. In those cases, the analyst usually would use an unsupervised learning technique, such as cluster analysis, to first come up with the clusters and assign each of the existing observations to a cluster or class. Then discriminant analysis can be applied to the new dataset with the assigned classes for the observations to develop classification functions that will help classify future cases into different classes. So here I mentioned something called classification functions. How the classification functions work will be discussed later in this lecture. As you can see in this example, sometimes the analyst would use a combination of unsupervised and supervised learning techniques to achieve the analytical goals. Discriminant analysis is popular because it is model-driven and provides us with insights about the model as in many classical statistical techniques. It is also found to be high performance when the assumptions of this technique can be met. We will discuss these assumptions later in this lecture. One may wonder what the differences are between discriminant analysis and the logistic regression, because both are model-driven and are designed for classification problems. Well, in addition to the different approaches that these two techniques take to classify, discriminant analysis has been found to outperform and be more efficient than logistic regression in many situations. That means you can build models that give you the same predictive performance with much less data using discriminant analysis compared to logistic regression. In addition, while logistic regression is useful when there are two classes, discriminant analysis can be used when there are more than two classes involved, making it more versatile in many business situations. Next, we'll discuss the basic concepts behind discriminant analysis. As a model-based classical statistics technique, the objective of discriminant analysis is to develop discriminant functions that are linear combinations of the independent variables that will discriminate between the classes. Let's first understand this objective. A discriminant function is usually represented as a mathematical function, and it is the linear combination of the independent variables, such as weight 1 times x1 plus weight 2 times x2 all the way to weight p times xp. You can think of the discriminant function as a dimension that best separates cases that belong to different classes. For example, if you look at the picture at the bottom right of this slide, with the bride and groom and the bridesmaids and the groomsmen all standing along a line. the people standing on the left side of this line are all female, whereas the people standing on the right side of this line are all male. This would be a good discriminant function because this dimension separates the male and the female cases perfectly. In other words, on this dimension, the two classes are separated perfectly, one on the left and one on the right. In addition, the line that is perpendicular to the discriminant function, in this particular case, the stair railing, happens to be the line that separates the two classes perfectly. So to identify the discriminant functions, we often use a technique called a linear discriminant analysis, or LDA. LDA creates new axes to maximize the separability among known classes. In other words, the new axes help to best separate the cases that belong to different classes. This definition often reminds people of the principal component analysis, or PCA, because PCA also creates new axes to represent data points. However, in PCA, we use the new axis to maximize the variability. Of the data, whereas in LDA, we use the new axis to maximize the separability. Of the classes. LDA gives n-1 discriminant functions. For example, if there are two classes, then there will be one discriminant function. And if there are three classes, there will be two discriminant functions. If you revisit the picture with the bride, groom, bridesmaids, and groomsmen, you can see that we only need one discriminant function, the line along which the people stand. But in the picture on the left here, where there are three classes, green, red, and blue, we would need two discriminant functions, which are called LD1 and LD2, to separate them. As you can see, we can separate the three classes fairly well with only LD1, because the classes that have high values of LD1 are blue cases, but some of the green and the red cases, which have low values of LD1, somehow overlap, making it difficult to separate them. So we use another axis, LD2, to help separate the green and the red classes. It turns out that among the green and the red cases that overlap, the ones with higher LD2 values tend to be green, and those with lower LD2 values tend to be red. Although this is not a perfect separation, it does help improve the separability of the classes a little better. As this example shows, LDA, or linear discriminant analysis, has another characteristic that is similar to PCA. Recall that in PCA, the first principal component would account for the most variability in the data, and more variability than the second principal component. And the second principal component would account for more variability than the third principal component, and so on. In LDA, the first discriminant function would best separate the classes and account for more class separation than the second discriminant function. And the second discriminant function would account for more class separation than the third discriminant function, if it exists, and so on. Now let's look at a relatively simple example to help you better understand these concepts. I have a small data set here that contains 20 records that are plotted on the scatter plot in this slide. The 20 records are 20 existing bank customers who were reached out by the Sunnyvale Bank about a home equity line of credit, or HELOC, offer. In this data set, we record the customer's age, income, and whether they responded to the home equity line of credit offer or not. The scatter plot shows the 20 customers in terms of their age and income, and the customers who responded to the offer are represented by the red dot. And those who did not respond are represented by the blue dot. Our goal is to develop a model to classify future customers into either the response or the no response groups using discriminant analysis. In other words, we want to develop the discriminant function that best separates the responders and non-responders. Since there are only two classes here, we will need to create n-1, which is one discriminant function. Now let's think about this intuitively. If I ask you to draw a linear line that would best separate the red dots from the blue dots, how would you draw it? Most likely, you're going to come up with a line that looks like this one, right? Although this linear line does not separate the two classes perfectly, it's the best we can do with the linear line in this case. The cases that are right to the line are all respondents, and the cases that are left to the line are all non-respondents except one. There is not another linear line that would be able to separate the two classes better than the one that we have here. And coincidentally, the line that is perpendicular to this best classifier is the discriminant function that would maximize the separability among the classes. Now let's draw this line and call it LD1. Since we have two classes, we only need one discriminant function, LD1, to separate the two classes. LD1 is the dimension on which, if we project the data points, we will get the most separability between the two classes. This may remind you of principal component analysis, or PCA. In PCA, we identify a new dimension that would maximize the variability of the data, and in linear discriminant analysis, we simply identify a new dimension that would maximize the separability between the classes. As you can see, on the new dimension LD1, most of the cases with higher values would belong to the response class, and most of the cases with lower values would belong to the non-response class. Now let's look at this diagram from a different perspective. Let's see what happens when the data points are projected onto the new dimension, LD1, as shown here at the bottom. As you can see from this slide, the diagram on the top is the original diagram with LD1 plotted. And the diagram on the bottom shows the data points projected onto the new dimension LD1. As we can see intuitively, the new dimension offers good separation between the two classes. The more the data points move to the right of the new dimension, the more likely it belongs to the response class. Just like the principal component scores in PCA, the values of the data points on the new dimension LD1 are weighted linear combinations of the original values. The software usually would generate the weights to create the linear combinations. The math behind the derivation of the weights is beyond the scope of this course and of no concern to users of discriminant analysis. So here I'm displaying the result from R that shows the weights derived from our dataset. As you can see, the weight for the variable age is 0.042 and the weight for income is 0.000021. As you can see here, the weight values are influenced by the scale of the variables. Since income values are in tens or hundreds of thousands, the weight value is relatively small. Based on these weights, we can compute the values on the new dimension LD1 for each of the cases. For example, for the first customer whose age is 44 and has an annual income of $99,000, this is how we would calculate its value on the new dimension LD1. And the value turns out to be 3.927. It's nice that we can calculate the values of the cases on the new dimension LD1, but more importantly, we need to understand how the software identifies the discriminant function. In order to maximize the separability of the classes, the discriminant function must meet two criteria simultaneously. First, the new dimension needs to maximize the distance between the two means of the two classes. Let's denote the mean of the classes as mu. The absolute value of the difference between the mu of the responders and the mu of the non-responders needs to be maximized in order to maximize the between-class variation. This part is relatively easy to understand. As you can see from this diagram, the farther away the means of the classes are, the more separated these classes are on this new dimension. And if you look at our diagram here, visually we can see that if the two mu's are farther apart, we can more easily tell the classes apart. The second criterion that must be met at the same time the first criterion is met is that the new dimension must minimize the variation, also called scatter, within each class. Let's denote the variation within the class or scatter as S. And S represents the within class variation. The more spread out the class is, the larger the within class variation. The closer the cases that belong to the same class are on the new dimension, the smaller the within class variation. So the idea of linear discriminant analysis is to identify a discriminant function that can simultaneously maximize between class variation and minimize within class variation so that the maximum separation between the classes can be achieved. And that is how the discriminant functions are derived. A common confusion about how the discriminant functions are derived is that it makes sense to maximize the between-class variation to create good separation between the classes. Why does it need to minimize the scatter at the same time? Well, let me show you what happens if the within-class variation is not minimized at the same time that the between-class variation is maximized. If you take a look at the diagram on the top here, we have a situation where the means of the classes are quite far away. Which offers good between-class variation. But the scatters of the classes are also quite large. Which does not offer small within-class variation. Visually, can we achieve good separation between the two classes on this dimension? Well, not really. It is quite difficult to separate the two classes on this dimension because the classes are too spread out, although their means are quite far apart. Because they are also very spread out, the cases that belong to the two classes are often mixed together, making it quite difficult to separate them. Now let's take a look at the diagram on the bottom. The same data points are projected onto another dimension. This time, the distance between the means of the two classes is much shorter. Than the diagram on the top. But the scatters of the classes are also much smaller. Can you now easily separate the two classes on this dimension? Well, obviously yes. You can separate the two classes perfectly in this case. This example shows you that only when the distance between the means are maximized and the scatters are minimized simultaneously will we get the discriminant function that best separate the classes. And this can be represented mathematically using the formula on the right. The numerator of the formula shows the squared difference between the means, and the denominator shows the sum of the scatters. Ideally, we want the numerator to be large and the denominator to be small. So the discriminant function that gives you the largest value for this measure would be the one that maximizes the between-class variation and minimizes the within-class variation simultaneously, and is the discriminant function of choice. Another way to think about this is that we want the discriminant function or new dimension to show classes that are very different from each other but very homogeneous within themselves. Well, what if we have more than two classes? One of the key advantages of discriminant analysis over logistic regression is that it can deal with more than two classes. So it is important to understand how multi-class situation works in discriminant analysis. As you can see from this illustration, we have three classes: green, blue, and red. And to best separate them, we need more than one discriminant function or new dimension. We need two discriminant functions, LD1 and LD2, to separate them reasonably, as you can see on the diagram. The larger dots represent the class centers. The idea is the same with two class situations. We want to identify discriminant functions that will maximize the between-class variation and minimize the within-class variation simultaneously. Since there are three classes, the between-class variation will be measured as the sum of the distances between the class center to a central point for all the cases. And then let's call these distance measures D1, D2, and D3. So the discriminant functions that can maximize the value of the sum of D1, D2, and D3 divided by the sum of the scatters S1, S2, and S3 are the best dimensions that separate the classes. In this case, since there are three classes, we'll have n-1 or two discriminant functions, as you see in the diagram. So this is how discriminant analysis works theoretically.